Wonderful. Welcome everyone. Thanks for coming back from lunch. My name's Lauren Blum. I'm a professor here at CU Boulder. I am up next on your agenda to talk about the Magneto-Ionosphere system. This is pretty broad. I'm supposed to cover quite a lot in not infinite amounts of time. And so I tried to touch on kind of things I found interesting. I know it's a pretty broad group of attendees also. And so some of you might be experts in some of it. Feel free to chip in on those topics. And then some of you might have never seen some of aspects. And so feel free to ask the, most basic, simple questions too. Any general announcements or we'll just start? Cool. Okay, wonderful. So a teeny bit more about myself. I work here at CU Boulder in the Astrophysics and Planetary Sciences Department, but also at the Lab for Atmospheric and Space Physics, or LASP. I was born and raised in New York City, so Boulder's really like the countryside for me, very rural. I studied physics in undergrad, took a year off to work at Los Alamos before going to grad school to kind of figure out if I wanted to go to grad school. I ended up getting my PhD from here in the aerospace engineering department, even though I kind of came from science and have continued in science. After that, worked at Berkeley briefly and then at NASA Goddard for a little while. And then I moved back here summer of 2020. Hindsight, not the best time to move back here, but really deep mid-pandemic, came back here for an assistant professor position at Boulder. My research is focused on planetary magnetospheres and particularly Earth's magnetosphere, energetic particle dynamics in the radiation belts here at Earth. And then I come at this from kind of an observational and instrumentation perspective, so building energetic particle detectors for CubeSats and smallsat missions. And you'll see some of these biases probably come out in this talk, both the Earth-based magnetospheric leaning and then also the kind of more observational perspective. I'm really interested in how we actually measure some of these things we know about the system and how we figure that out from an observational perspective, not just from the fundamental physics. Okay, I think this is an older version of my talk because I uploaded it yesterday so that I would obey wishes, but then again this morning. I can use this version if that's the easiest, but if there is a quick way to update it, that might be smoother. Yeah, this one looks great. Thank you. Okay. Okay, so today we're talking about planetary magnetospheres and ionospheres, and I did look at the rest of your speakers, and it looks like Bob Marshall is going to talk about ionospheres in quite a lot of depth, and he was really on top of things and uploaded his slides, and so I skimmed through them, and so I'll mostly focus on magnetospheres and touch a little bit on ionospheres as well, but I didn't want too much overlap there. So we'll talk about what they are, what they look like, kind of the parts that make them up, and then also how they behave. We'll really primarily focus at Earth. Oops, I'm practicing this fancy pointer. Let's see if I keep using it. But then I think throughout the talk, try to keep in mind how this would vary in other systems, what this looks like at other planets or in other stellar planetary systems. And what happens, when you change some of the variables of our system, if you change planet size, mass, rotation rate, solar wind driver, what does that do to the system? And like I said, I like to think about how we actually observe these regions and processes. How do we know what we know about the system? And then I also wanted to focus and highlight a bit on kind of the interfaces and cross-region coupling. So people sometimes say, oh, I'm a magnetospheric physicist, I'm a solar wind, I'm an ionosphere person, but there's a lot of overlap between these and the system is very interconnected. And so understanding the kind of coupling across these regions is really important. And because I think the theme of your this year's summer school is comparative systems, I thought I'd focus a bit on comparative magnetospheres here. And there's this quote now from a while ago, but the Geospace Environment Modeling Workshop, GEM workshop in 2010, where Margie Kivelson, a planetary scientist, talks about kind of why you want to study comparative magnetospheres. And typical of the rigor of physics is the need to change the parameters governing the system studied in order to test whether behavior varies as predicted. And so, you know, as experimental scientists, we want to turn a knob and see if we know what will happen. And that's difficult to do in space. You know, you can't actually go out and change the magnetic field strength of Earth, but you can find systems that have different variables, and through that both better understand the processes going on at Earth. You know, do you really understand what's going on? Can you predict it if you change something? And then also use what we know about the Earth-Sun system to understand other planets and exoplanets or stellar planetary systems. Okay, that being said, I'm gonna do exactly what I said not to do and pigeonhole all of you, but I kind of wanted to get a sense of what everyone studies and works on. And again, you'll see some of my bias that I lumped solar and solar wind together here, but gave Earth's magnetosphere its own bullet. But I just wanted to get kind of quick show of hands of who studies what. And you can raise your hand multiple times if you think your research really, you know, includes multiple areas here. So solar, wind, lots, okay, great. Earth's magnetosphere, okay, cool. Earth's ionosphere, atmosphere, lower down, great. How about other planetary systems? Okay, nice. And any others that I didn't actually cover on here? I didn't want like a million bullets, but everyone raised their hand at least once. Okay, wonderful. I also, instead of just talking at you forever, I wanted to start with a quick little discussion on, you know, why should you and whatever your specific research area interests are, learn about some of these other regions. And so I'd ask all of you to kind of think about what your research is. Think about either from that list I had up there or general space environment, what's another region that's kind of seemingly unrelated, and think about, you know, why should you care about it deeply and how might it impact your own research. And so I do this a lot, especially for this talk. Sometimes people talk about the ionosphere and I just kind of glaze over, and there's lots of different you know, molecules and different things that I don't want to know about. And then I try to think about how it relates to magnetospheric research and the radiation belts, for example. So I'd say chat with your neighbors for like 2 minutes, talk about what your research is, pick a different topic and why it's not so far and unrelated as it might seem. And then I'd like to hear a little bit about what you discussed. So take a few minutes. Okay, I know you can all talk about this for, you know, the next hour, but we'll bring it back in, and I'd love to hear, you know, if anything came up in your conversations, any connections that you made or didn't make. Yeah, does anyone want to share? Thanks. Thank you.
One thing that we talked about is that, you know, a lot of these different subfields within space weather, whether it's magnetosphere, ionosphere, whatever, you know, we all use similar techniques, but in different ways. A lot of the problems are the same, but they're specialized to the field that we're in. So like I was at COSPAR and I do stuff with the Aurora, and I was actually in a solar flare talk, and the technique they were using to analyze these solar flare ribbons, there's like these little beads that form sometimes right before the flare onset, is the same technique used to work on auroral beads. And I thought that was really cool. So
that's a great point. Not just how does the science connect, but how do the techniques we use really, you know, medical imaging versus solar imaging. Yeah, cool. Did you have I think we're supposed to pass or toss this little thing. Yeah, thank you.
Fine. So it's about for the magnetosphere, there are the two sources of the charged particle that's are coming. One is sun and other is our ionosphere. So it's either, and everything in magnetosphere is matter for us, whether it's low energy electrons or it's high energy electrons. So that's why it's there.
Yeah, great. I'll have a few slides that kind of repeat that, the sources of what's filling our magnetosphere and where they come from. And I think keep in mind, you know, at Earth, like you said, solar wind and ionosphere, but at other planets, it might be different. Yeah. Anyone else?
And if you're somebody who hasn't used the box yet, maybe you should volunteer.
Don't have to though. Yeah, great, thanks.
Hi. Well, I was once reading a book about the solar physics and atmospheric physics, and in the book they made an idea that studying the Earth atmosphere, it's a very good analogy as an introduction to study the solar atmosphere, because there's some layers of both atmospheres that are partially ionized, not completely ionized.
Yeah, excellent. Okay, thanks so much. We'll keep moving, but I liked a few of the things I heard, you know, both about how the physical processes interact, also how our techniques overlap. And then over at this table, there was some discussion of like, you know, even if you're studying the sun and it doesn't actually, it's not affected by Earth's ionosphere, that might be how you can sell your science or motivate it and make it more interesting to, you know, what's actually important about solar physics that is important to ionospheric scientists. So I liked that way of thinking as well. Okay, so thank you again for sharing. A few notes as we move forward. Please interrupt at any point. I would much rather hear from you all than just talk at you for forever. Questions, comments, things you know about from your own research, if you're an expert on something we're talking about. And then my hope, again, throughout this whole program is that you'll learn a lot from each other, not just myself or the speakers that you have. And then the other thing to keep in mind that actually Fran mentioned to me was kind of as we go through this, think about what the common questions or misconceptions might be about some of these systems. And so as I've taught some of the kind of intro undergrad courses here at Boulder, I always like it because students come up with questions and you're like, oh, I didn't even realize that that's like what you would assume. And so like space is empty. And I'm like, oh no, there's all these interesting particles filling it, but that's kind of what you hear about. And so please think about that as we go through, add any that come to mind. And then also, you know, if you've never understood something, please jump in. So another one that's kind of more I get from grad students a lot is that Earth's radiation belts, that the particles come all from the solar wind, that these kind of high energy particles come directly from the sun, enter the magnetosphere and make these regions of very high energy particles. And it's not quite that direct. The particles kind of circulate through the system for quite a while, can be from the ionosphere or solar wind and get energized through a whole number of different processes on different timescales. Okay, so yes, I hope to hear from you throughout the next hour. So I thought I'd start with kind of very general definitions. What is a magnetosphere? And if you look this up, one of the ones that you often get is that it's this volume of space that's carved out of the solar wind by the planet's magnetic field, formed by the interaction of flowing plasma with a magnetized body. Does anyone see any modifications we might want to make to this definition, just right off the bat? Yeah. Yeah. Yeah, wonderful. So this assumes that the planet has an internal magnetic field, but we often talk about magnetospheric dynamics of induced magnetospheres. Things like, you know, or systems like Mars, which don't have a global magnetic field, but little crustal ones. And so even this basic definition, we might revisit or modify depending on what system we're talking about. But at Earth, the magnetosphere is really dominated by two influences: the internal magnetic field generated by dynamo processes inside the core. And I think you'll have a number more lectures on actual dynamo physics and how this happens, both at different planets and stars. And at Earth, this is roughly dipolar, a dipolar magnetic field. But it is important to note its magnetic field is offset from the Earth's center and tilted from relative to the spin axis. And so this actually introduces lots of details to the solar wind magnetosphere interaction and magnetosphere ionosphere atmosphere interactions. And then this internal magnetic field gets distorted by the solar wind and what's coming from the sun. And so we often get on the sunward side of the magnetosphere this kind of blunted, compressed region, and then on the anti-sunward side, a stretched, elongated magnetotail. And this is talked about as the night side of the magnetosphere versus the day side. And again, at Earth, like the processes and environment on the day side can be quite different than those on the night side of the magnetosphere. It's really organized a lot by where the sun is relative to Earth rather than necessarily the latitude, longitude you are at Earth, which is spinning underneath you. And again, that's somewhat different at different planets. Just for reference, here's low Earth orbit, geosynchronous orbit, in a very crude, crayon scale. Anyone, just to place the lunar orbit on here? Anyone know where it would be? Units of Earth radii or other? 60, wonderful. So that is, upstream in the solar wind on the day side, but in the magnetotail on the night side. So you can get interesting kind of variable plasma environments at the moon because of this. Okay, here's, a cartoon of the magnetosphere, all the different component, well, not all, some of the different constituent components. I'm always looking for better versions of this. So if anyone has a favorite magnetosphere cartoon, pass it along. But this is looking from the side on. The sun is over on the left, north and south poles of the Earth, and then day side compressed and night side elongated. Okay, so when I was looking up magnetospheric systems, I came across this paper from a few years ago called The Joined Up Magnetosphere. Does anyone know what this is a picture of? Yeah, starling birds, yes. And they kind of make these weird swarms. And this paper actually kind of compares this system of starlings to the Earth's magnetosphere as this kind of interconnected system of systems, how a little movement over here can ripple through the whole thing and affect things over here. And these birds make these kind of crazy shapes and morph, and I think it's for to scare predators off, that they can act like this large being, even though they're made up of individual small little edible birds. And then this paper also made a kind of nice comparison, or maybe a bit of a stretch, that both these swarms of birds and our magnetospheric system can disrupt power lines. And so I liked that these birds actually sit on power lines, and just the sheer weight of that many birds can knock them down, compared to geomagnetically induced currents at the magnetosphere that can also knock out power grids. So I liked this comparison as I was looking for kind of general, what is the magnetosphere, how does it behave? Because we're going to talk about all these little different regions that are named different things, but I think keeping in mind the big picture is important throughout. Okay, so starting at the very front, what happens when the solar wind actually hits the magnetosphere? You get a shock, which is known as the bow shock. This bow shock is different at different planets. Looks different depending on both the solar wind driver and the obstacle it's impacting. Just like you can get different shaped shocks for different obstacles here on Earth. And so what are some of the parameters that actually control this shock shape? People want to jump in? Yeah. Speed of solar wind, yep, definitely. Size of the planet or obstacle, yeah, airplane, yes. Yep, wonderful. Density of the solar wind, yeah, great. Yes, yeah. Orientation of, well, for starters, whether there's a magnetic field that the obstacle has, but then also how it's pointing, yeah, wonderful. Oh, and the solar wind magnetic field direction, yeah. Yes, great. Yeah, yeah. Rotation of the planet obstacle for shock shape. I actually don't know if that would be a major player. Yeah, I would think that might come into play more in how the solar wind couples to the magnetosphere, what processes, but whether or not you have bow shock might be more, magnetic field strength at some distance. Yeah, if the magnetic field is very offset from the spin axis, then the rotation will change that shape pretty dramatically. Yeah. Okay, wonderful. Oh, one we didn't get to. So related to the assumption of whether the body has a magnetic field is whether it's conducting or not. Then if it does have a magnetic field, Mach number of the solar wind, so all those properties, speed, density. That last one also relates to kind of what the planet is emitting and maybe most important if it's not dominated by a large magnetic field. Yeah, wonderful. Okay, so once you get to the shock, we get just behind that, closer to Earth is the magnetosheath. And so that shocked solar wind continues on towards the Earth, but it's denser, hotter, and slower after the shock. And then as it flows around the obstacle, around the Earth, it expands, cools, and speeds up again. So Earth is not sitting in pristine solar wind. What's hitting the magnetosphere has been through this shock and the properties have been changed. And I thought this was a pretty cool visual of the magnetosheath. Whether or not it's totally accurate, yeah, debatable. But I think it's a nice reminder that one, the solar wind properties are not what's hitting the Earth. They get morphed and changed. And then you can also have lots of kind of fine scale or mesoscale structure within the magnetosheath that actually couples to the magnetosphere. Things like plasma jets and bubbles and different shapes that actually impinge on Earth's magnetosphere. Okay, so then you actually get to the magnetosphere and its outer boundary, the magnetopause. Where this magnetopause is determined by pressure balance, pressure in the solar wind versus pressure inside the magnetosphere. And at Earth, we often make a lot of assumptions based on the various variables here and their values. And we can simplify this equation quite a bit and assume the dominant pressure in the solar wind is this flow pressure, whereas the dominant pressure in the magnetosphere is magnetic pressure. And when you do this balance, you come up with a magnetopause distance at Earth around 10-ish Earth radii, 6 to 12 maybe. And of course, changes in the solar wind can change this quite a bit. Is this what we'd expect at other planets as well? Any ideas? I mean, the physics should hold. The top equation should be true, right? Pressure balance. But maybe, yeah. Yes, so at Jupiter and Saturn, there's a large internal plasma source from the moons and satellites. And so that creates more thermal pressure within the planetary magnetosphere that we don't have here at Earth. Yeah, great. And I imagine Fran is sitting back there that she will talk quite a bit about this later in the week, doing comparative magnetospheres. And this is actually stolen from one of her tutorial slides a while ago, but you see that the size of the magnetosphere at Jupiter and Saturn are inflated relative to just the magnetic field strength and solar wind properties that you'd expect there based on this internal plasma source from the moons and satellites. Okay, so like we spoke about, Earth's magnetosphere is not empty. It's full of charged particles, neutral particles, ranging in energy from low to high, that are all trapped in the system by the magnetic field. Sources of this plasma, do we know where they come from? We heard earlier solar wind and ionosphere are the two primary sources at Earth. And the relative importance of these at Earth is highly debated. It's kind of a current question, as well as how the solar wind actually enters the magnetosphere and contributes to this population. So while we know the general two sources, when one is more important, when the other is more important, how they fill the system are all open questions. Does anyone know how we actually know this? Like, how do we know where the particles are coming from in the magnetosphere? An electron sitting out in the plasma sheet is an electron. It doesn't have like a name tag where it came from. Does anyone know? Yes, so I heard particle species, O+, and then also energy, yes. Energy is a tricky one because once it gets into the system, it can kind of be circulated throughout, you know, that's what these little arrows are supposed to show, that it's moving throughout the system, and it can happen, this circulation can happen on repeat. And so while the initial energy might be a good tracker, then later on, if you're measuring it post-circulation, other processes might have changed it. Composition is one that is harder to change through the recirculation. And so there are a number of papers by Lynn Kistler where she's used kind of ion composition measurements in the magnetosphere. And you can attribute some of them to Earth's ionosphere, nitrogen, for example, or O+, whereas some are from the solar wind, like helium double plus or higher ionization states of oxygen, which are hard to get in the ionosphere. And so by tracking the ratios of these different ion constituents over time and space, you can kind of get an idea of where plasma has come from and how this changes throughout geomagnetic storms or other time periods, which I think is pretty cool. Okay, again, would we expect the same at other planets? Ionospheric source, solar wind source. Yeah, so internal other source, yep, moons. Is solar wind always a source? Yeah, so should be less of a source depending on distance from the sun and also how that coupling between solar wind and magnetosphere happens. And so if there's easy access versus more difficult access, that should change as well. And since, not to put Fran on the spot, but has this been done at other planets of trying to track solar wind contribution to magnetospheric particles versus internal? Excellent. Mm-hmm. Mm-hmm. Great. Yeah. Okay, excellent. Okay, so moving into these once the plasma's in there, what does it look like? At Earth, you often hear about all these different plasma populations and different particle regions, things like the plasma sheet, the plasmasphere, radiation belts. Some of the main ones that get categorized are plasmasphere, which is close to Earth, high density, very low energies, and this co-rotates with Earth and primarily comes from the ionosphere. It's so low energy. The ring current, kind of medium energies in the keV energy range here at Earth, creates a current around the Earth based on ions drifting one way and electrons drifting the other. And then at the highest energies, the radiation belts, it's kind of MEV type energies. So you're jumping up by orders of magnitude for each of these. They occur in slightly different regions, but kind of all overlap, which is why it's difficult to make cartoons of them. And also, you know, these categories are slightly artificial because there's a fair amount of overlap between these energy ranges and regions that the particles occur at. So what's kind of upper level ring current versus lower level radiation belt are hundreds of keV electrons. Where do they fall? That's one that even within the radiation belt community, sometimes people consider them radiation belts and other times not. And so I thought this was kind of a nice, again, you know, oversimplified cartoon of kind of where these different particle populations land in terms of energy or temperature, but also density. The other thing this shows is that there's quite a wide range of both energies and densities that particles span within the magnetosphere, making it very difficult to measure. And so if anyone works on instrumentation, often an instrument can only measure like a fixed range of let's say, electron density or flux. And so to actually capture this whole range of particle populations, you often need lots of different instruments to cover little chunks of the energy spectrum. And so this is just an example from the Van Allen probe's MagIce instrument, which actually was made up of 3 different instruments so that they could really capture the full dynamic range of expected density of electrons over this energy range. So from an observational perspective, this makes things tricky. And even trickier if you aren't just talking about the inner magnetosphere. So if you're something like the MMS mission that measures magnetosheath, but also magnetosphere and magnetotail, the range of different particle environments you fly through and have to try to capture is quite broad. Okay, so moving even further down, I didn't want to totally exclude the ionosphere. As we move below radiation belts, ring current, and Earth's plasmasphere, the source of the plasmasphere comes from the atmosphere and ionosphere. And you often see these kinds of plots or pictures which show altitude on the y-axis. And then what we're seeing here in the middle is neutral gas temperature. So that's the atmosphere, the neutral gas. And then electron density, the ionosphere, so the ionized portion of the atmosphere. And you can see there are different layers in the ionosphere, the D region, the E region, the F region. There are different regions of the atmosphere, thermosphere, mesosphere, stratosphere, and there's often changes in temperature at these boundaries, changes in temperature and density. And what you can see is that there's variability in these profiles. And so this, for example, I believe is solar minimum and solar maximum. You can see how this changes depending on solar driving. I stole this from a previous tutorial on the ionosphere because I thought it was nice to actually put ionosphere and, you know, ionized and neutral particles on the same plot. And you can see the ionosphere is actually a weakly ionized plasma, that neutrals really dominate at low altitudes in the few hundred kilometers and even further up than I imagined. And that these ion neutral collisions can really strongly control the dynamics of this region. So the fact that you can't just assume everything is ionized makes things a lot more complicated, and part of the reason I like to stay at higher altitudes. The other thing to point out as it relates to figuring out plasma sources in the magnetosphere is actually the composition of our atmosphere, and how this changes with altitude. And so N2 and O2 are really dominant here at Earth. As you move up, you get lighter hydrogen helium particles. And then the rest of this, I think you'll have a lot more math based on Bob Marshall's slides, so we'll skip some of that. But really just the composition of Earth's ionosphere and atmosphere, and keep in mind at other planets, this will be potentially quite different. And then this is just to highlight the variability that both the temperature profile and the density profile are highly solar cycle dependent. And they're both inflated at solar maximum and smaller at solar minimum. And why I care about this, I'm sorry, this is a little pixely, but this strongly affects how satellites fly through this region, and how atmospheric drag changes the orbit of a satellite in low Earth orbit. And so I have used data from the SAMPEX satellite here on the left. And the reason I liked this is it was up for 20 years, so you actually get solar cycle variation. And you can see that the altitude of the spacecraft, the slope of the change is like noticeably different during solar maximum here near 2000, and then at the end of life in 2012. That the decay in the orbital altitude is much steeper during solar max than solar min. Okay, so let's pause again. We've talked about this a teeny bit, but because I like the magnetosphere and find the ionosphere complicated, messy, I'd love you all to think specifically about Earth's magnetosphere and ionosphere and how they're connected. And how does the ionosphere affect the magnetosphere? How does the magnetosphere affect the ionosphere? What are the processes that are important here, and why might one person care about the other? So we'll just take 2 more minutes, talk at your table. I'll walk around. Okay, let's regroup. Does anyone want to share some of these processes that came up? Yeah, this table. Wonderful. We'll start here. Yes.
Can you hear me?
Yeah.
So I was talking to people in my table. I look at how they say reconnection causes enhanced convection in the magnetosphere or substorms. And when I look at these phenomena, I use geomagnetic indices that are measured by ground magnetometers. But here it's important to note that this enhanced convection in substorms actually give rise to currents in the ionosphere. These currents then cause magnetic disturbances, which is what the magnetometers pick up.
Yes.
What I'm doing is literally just looking at magnetospheric phenomena using ionosphere.
It's fully based on current systems. Yeah, wonderful. Yeah. There was, I think, same table and then, oh.
Sure.
So I do Aurora stuff. So, I mean, literally, like, if you're ignoring what the Aurora is, I mean, the Aurora tells you what's going on in the magnetosphere a lot of times. So, yeah.
Yeah, wonderful.
Over to this table.
I won't call on anyone.
I guess I would just say that it's sort of, it's the internal boundary for the magnetosphere. So whether or not the ionosphere is particularly conductive or not changes how, say, waves generated in the magnetosphere propagate and bounce back. It also changes how easily field lines can be dragged through the ionosphere, which again affects things like substorms.
Yeah. So that ionospheric conductivity controls a lot of magnetospheric dynamics, but also magnetospheric processes can control and modify ionospheric conductivity. So it's really feedback there. Yeah. Any other? Yeah.
It's about ionospheric outflows and how they contributes to the reconnection rates in the day side as night side. So that's important where the ionospherics contribute to the magnetospheric phenomena.
Yeah, wonderful. So how the ionosphere feeds plasma out into the magnetosphere, how that plasma can then affect reconnection rates, which we spoke about at this table a bit. And then also there has been a lot of recent interest in these ionospheric outflow and upflow processes and where they put particles in the magnetosphere, only in the distant tail, or can they directly place particles in the inner magnetosphere? So a lot of open questions there too. Okay, anything we missed? Major ones? Yeah. Yes. Yeah, so one way is that the ionosphere feeds Earth's plasmasphere, this kind of cold, dense plasma in the inner magnetosphere. During storm times, the plasmasphere gets eroded and you get these plasmaspheric plumes reaching out towards the day side that can actually reach all the way to the magnetopause. And so this is a kind of relatively localized, large enhancement in the total density at the reconnection site, which can actually decrease reconnection rates. And there's been a lot of modeling as well as observational attempts to see this, this effect in reconnection rates based on cold plasma density. Yeah, excellent. Okay, the other one that sort of touched on with aurora, but particle precipitation from the magnetosphere can change the conductivity of the ionosphere, can create beautiful things to watch, and can also change atmospheric chemistry even. High enough energy particles reach down into the atmosphere and ionize particles. So that's one of the more direct connections in my research. We'll skip this. This was a kind of maybe nice cartoon I found that shows all these processes, how they interact, how the different regions connect through different, yeah, I don't know if it helps clarify anything or just show how complex the system is, but thought I'd put it in here. Any other questions up till now? Stuff we've talked about? Okay, if not, did you have one? Oh, yeah. Yes, a little bit. Yeah, and how about, yeah. Ooh. Yes, so this relates to all the different weird terms we use to describe slightly different particle populations in the magnetosphere. And so I touched on the very main ones. Was it here that you saw it or earlier? Okay. Okay, there's the plasmasphere, cold, dense. Often there's region just outside the plasmasphere that is just a teeny bit warmer, but still cold. Sometimes more oxygen dominated. As you move even further out, there's the plasma sheet and then lobe plasma, and sometimes there's some layers in between there. The warm plasma cloak, I think, is that layer just outside the plasmasphere that is, yeah, a teeny bit warmer, sometimes a different composition, and not always present, and not always at all local times. So you can get kind of slightly warmer plasma just beyond the cold, dense region that can affect what waves grow there, how waves interact with particles, just overall system dynamics. Yeah, but it might be, was it on that big list of different yeah, you'll see it's just like right next to other ones. And so whether you pull it out or not is personal preference often. Yeah. Mm-hmm. Yes. Yes, there absolutely is. And I actually, if we had stuck with my older version of my slides, that was included. But I looked at the time and the number of slides and decided to remove it. But the cusp is very important, especially for kind of solar wind magnetosphere coupling, as well as so particles can come in through the cusp very easily because it's kind of a direct access point. They can also leave through the cusp, and so as a source of low altitude particles that make it out into the magnetosphere, the cusp is important on both of those. There have been a lot of cool rocket missions that go through the cusp, measure these particle populations. And I think the Tracers mission, upcoming SMEX mission, will fly through the cusp and kind of look at how reconnection on the day side changes the particles flowing in along the magnetic field into that cusp region. Yeah, I skipped a bunch. I skipped a ton. Yeah. Okay, so in the last bit, we've been talking about kind of the static picture of the magnetosphere a lot. I thought I'd touch a teeny bit on the dynamics because the system, the whole thing is changing in time and space. There's, like we saw, particle populations spanning many orders of magnitude. And then we'll talk a little bit also plasma waves spanning full range of frequencies. And then the system is responding to changes in the driver, the solar wind, on timescales of seconds to years. And so you can look at the very short-term rapid changes in the system and also the kind of solar cycle ones. Yeah. I think this is density. And so you can see the magneto sheath on the day side gets orange, gets denser than the solar wind. And then in the magneto tail, those lobes are often very low density, the kind of darker blue regions. Yeah. Mm-hmm. Yes, I think this is sped up for visual purposes. And so the actual time scale versus what we're watching it at, same as like auroral movies are often sped up. This would be much enhanced. So you can kind of see the solar wind. Maybe you can see some magnetic field lines changing direction and a little bit as the driver. So that here is on less than second time scales. Often solar wind changes in density and pressure and magnetic field direction we look at are kind of on minutes or larger scale, kind of a kernel mass ejection or high-speed stream would be long, tens of minutes. And so this is sped up significantly. I don't know what time, 100 times maybe? Yeah, great question. So the flapping of the magneto tail, while it can change rapidly, this is over-exaggerated. Yeah. Okay, so some of these changes that drive this, like we talked about often in the solar wind, things like coronal mass ejections, high-speed streams, which I think other talks cover more, can cause geomagnetic disturbances. And the two main ones we talk about are geomagnetic storms, these kind of global disturbances of the system that last days to many days, versus substorms, which are shorter, kind of more hour timescales and often more localized. And so some of the ways we measure these are ground-based magnetometers. And so for geomagnetic storms, the DST index or SIMH index is put together by magnetometers primarily around the equatorial region. So they really only pick up large-scale global disturbances, whereas auroral electrojet measurements of substorms are at magnetometers at higher latitudes that can respond to kind of more localized dynamics in the tail region around the night side of the magnetosphere that might not be a large scale disturbance. One example of these timescales is the radiation belts. So here we're looking at kind of a slice through the equatorial plane on the y-axis. This can be thought of as units of Earth radii away from the Earth. And color is the intensity or the flux or density of these multi-MeV energy electrons. And what you can see over this kind of few week period are 3 geomagnetic storms at the bottom. And each one causes like a very dramatic change in the energetic particle population in the outer radiation belt on timescales of hours to days. And sometimes it causes, large enhancements like the last one, sometimes big depletions like the middle one. So often we study changes in the magnetosphere on kind of substorm storm timescales. But I do like to think about decades-long changes as well. And so this now is that same kind of, distance from Earth on the y-axis, and now over a 20-year period. And you can see the change in the kind of net content of the outer radiation belt over years and how it varies with solar cycle. And one thing to note is that actually solar maximum is not necessarily when you have the most enhancement in the outer radiation belt. It's really the declining phase of the solar cycle when you have a lot of high-speed streams in the solar wind that pump up the radiation belt content. And the other thing that's kind of nice about this picture is you can see that this last solar minimum, or not last, but the one here at the end in around 2010 was a very deep minimum where the radiation belt was extremely quiet and almost, depleted for year timescales. Yeah. This is based on SAMPEX measurements. So like I showed again, we have 20 years of SAMPEX. And then actually the last few years, so SAMPEX re-entered in 2012, and this is a plot from Shinlin Lee. The last few years are stitched together with a CubeSat measurements also from low Earth orbit. So he kind of overlaid those to extend the measurement period. Mm-hmm. Mm-hmm. Yeah, so the question is, why at solar maximum is the radiation belt not most enhanced? And it could be there's less acceleration or more loss. And so loss through the magnetopause, if coronal mass ejections are really compressing the magnetosphere, you might get a lot of loss out there. I think studies that have looked at this have found that high-speed stream type storms tend to cause a lot of acceleration because they last so long, the recovery phases. And that that acceleration tends to be what contributes to this kind of offset maximum. But the loss is probably, I think it's hard to measure. You only have one measurement and you don't know what's actually net loss versus acceleration. Yeah, yeah. Yes, that's the Halloween storm. Yes, yes. And so you can actually see like individual storms on this that really injected particles way down close to Earth below the outer radiation belt. Yeah. And I think if this extended through this spring, you might see our large May storm coming in also. Yeah. And also cool to overlay on this, this is the DST index. That's like smoothed and averaged over month periods. But you can really see just how quiet that last minimum was in aggregate. And also how that radiation belt tracks DST index, which is kind of cool. Okay, so we'll keep going. So how the solar wind actually couples into the magnetosphere and drives geomagnetic activity, storms and substorms, is highly dependent on the orientation of the interplanetary magnetic field and whether it's northward, the same direction as Earth's magnetic field, or southward, oppositely oriented. And for southward, you get reconnection and an open magnetosphere, so kind of more direct entry of solar wind into the magnetosphere versus the northward configuration that's a closed magnetosphere, at least in the cartoon version. Although you can also get oppositely oriented magnetic field over by the cusps in this configuration. So it's somewhat oversimplified to say it's just closed or open. you might get reconnection happening, just not at the subsolar point. Mhm. Mhm. Yeah, yeah. Yeah, so in the large scale picture, it's actually impressive that it does, it is so closely related to pristine solar wind IMF direction. But this is also why it's so difficult to predict whether you'll get a geomagnetic storm, the size of it, and the response of the magnetosphere just based on solar wind measurements, because you don't know how that magnetic field changes once it moves through the sheath. And so large scale picture, you can kind of often see after the fact, oh, we got a really big geomagnetic storm. IMF BZ was southward for a while, or it was northward, we didn't see much. But on the smaller scales, this is why it's so difficult. Yeah, yeah, yeah. Mhm. Mhm. Yes, so you, right, it's not just always going to be southward for hours and then turn northward for hours. If it's rapidly fluctuating, you'll get kind of turning on and off, and so you might get more bursty reconnection. You might get, if you look at the DST index, actually, you know, the classic picture of a geomagnetic storm is this big dip and then slow recovery, but actually you often see a lot of variability. Mm-hmm. Yeah, so the cartoon picture is messed up by all these details and reality, very much so. Yeah. Yeah. Okay, so if you do have southward IMF and reconnection on the day side, you get this Dungy cycle, which I have heard there are dances that depict it, but I am not going to do them. But you can kind of track the magnetic field lines as they move. And so here, blue is pure solar wind, red is pure, you know, both foot points at Earth. And purple is once they've reconnected, if one foot point is earthbound and the other is in the solar wind. And so if you kind of step through these panels, A, B, C, you start with the two on the day side, you get reconnection. And then since the solar wind continues to flow about the Earth, it drags those foot points. There you go. Drags those foot points back into the magneto tail. Where they can pile up in the tail and reconnect again. There you go. Yes. Okay.
Okay. So my question to you is, how fast is the solar wind, roughly? 400 kilometers a second? What is the size of, how long does it take the solar wind to go 1 Earth radius or 1 Earth diameter? (6,400 kilometers for the radius, right, of the Earth? Okay. Shout out when you got a number. Think in your head, is this 2 seconds, 20 seconds, 200 seconds, 2,000 seconds? 120? Okay, so that means 2 minutes? 2 minutes to go a radius or a diameter? Which? Doesn't matter. Okay. How many?
We're getting a lot of different numbers thrown out
Okay.
here.
So we're talking couple of minutes to go a diameter. What was the size of that thing, of your movie? How
Like
many?
the magneto, like where
So,
this is
so if
happening
you
in the
go
magnetosphere?
upstream, it's
Mhm.
10 Earth radii, right? So that's 5 diameters. And so how many seconds to go from here to here? That's 10 radii. 157 seconds, which is how many minutes? 2.5. So reconnection takes, you know, the whole cycle, the whole Dungey cycle, go down to the tail. 15 minutes, 20 minutes?
Yeah, it'll depend actually. How far down tail it actually has to go to cause this reconnection. And so there's a fair amount of discussion of where that reconnection in the magnetotail is happening. Is it near Earth or deep distant tail, or is it multiple places in the tail?
So in order to keep the Dungey cycle running, you've got to have this orientation for the whole cycle, right? So that means that your disturbances upstream that generate this Dungey cycle have to remain persistent for tens of minutes, maybe even as much as an hour, right? Keep this in mind next Thursday when we start talking about other planets, particularly really big planets. Okay, just something to think about. We'll come back to this.
Thank you for interpretive dance. Okay, so yes, where in the sounds good. Where in the tail this reconnection is happening is under debate, and one of the things the Themis mission has been trying to get at. The other thing to point out is, you know, this again is the cartoon picture looking side on. It's nice and clean. There's, you know, simple purple, red, blue, and they cleanly move from one to the other. Global simulations, these are MHD simulations now looking down at the equatorial plane with the sun over on the right-hand side. And the color, the kind of pink blue color is the magnetic field in the Z component. And you can see that it's not just like one clean reconnection point in the tail and then things smooth beyond that. And within that, there's all these weird little fingers happening and kind of mesoscale structure that occurs in the tail and the night side of the inner magnetosphere that can make this global picture much more complicated. Okay, and so if we just return to that cartoon picture again, if solar wind is not southward, if we go to the northward picture, it's closed, but there can still be entry of solar wind into the magnetosphere and interaction between those two regions, primarily through Kelvin-Helmholtz instability on the flanks. So this kind of solar wind streaming past the magnetosphere, you get an instability in these vortices on the sides that can both particles can directly enter through. They can also set off all sorts of plasma waves that can then change the system as well. And I was just, I stuck this in here because I was just like looking at recent papers and this came up in my inbox this morning that this kind of model of where you might get this viscous interaction at Uranus, and they also do Neptune, and how that varies based on solar wind magnetic field strength, which you'll notice very small in both these cases, season, whether the, so at these planets, the spin axis is highly tilted relative to the sun-planet plane, and the magnetic field is also highly offset from the spin axis. So you have to take into account both those angles when you consider this interaction. And so they had this nice model showing where you get, where you can get Kelvin-Helmholtz instability, where it is allowed in pink versus where it is not allowed in black, and how that varies. I thought was cool. Okay, and then through these dynamics, we've talked a lot about particles, but geomagnetic storms and substorms can also generate all sorts of different plasma waves, different types of waves occurring in different regions that can interact with different types of particles, energize cold plasma, accelerate hot plasma to become the radiation belts, scatter particles in pitch angle and cause them to enter Earth's atmosphere and be lost from the system. So waves can really connect different particle populations and change the dynamics of the system quite dramatically. And again, this is the pretty cartoon that we see. Every wave is, you know, in its neat little place. But when you actually look at the wave data itself, it's a mess. There's overlapping wiggles, electromagnetic, electrostatic at all different frequencies. And so those of you studying plasma waves will have seen this in your data. Okay, and lastly, we hadn't talked much about the aurora, but one of the ways we map these magnetospheric dynamics and one of the kind of visible illustrations of substorm dynamics is through the aurora. And so we'll skip this. Oops. Thought I'd highlight why I like the aurora. Did any of you see it in May during this last major storm? This was a movie, I'll credit Longxi Gan, who's postdoc at Boston University, but here in Boulder. And he just went into the foothills and took this video with his phone and a tripod of the aurora over Boulder, which I thought was really awesome. And yeah, you can see all the kind of dynamics and kind of, yeah, different colors, different, yeah. It's also amazing that his phone could do this. Okay, the other reason I like aurora, it was one of the kind of early manifestations of magnetospheric dynamics. So there are these great old papers of like hand-drawn, someone staring up at the sky, drawing little wiggles and curtains that they see and how they change throughout the course of a substorm, and trying to figure out what's going on in space from this, this kind of projection of it on our atmosphere, which is pretty cool. And then lastly, it's universal process. So we get aurora at different planets, and it can tell us about the processes going on there. It can act as a map, so you actually know where the moons are mapping to in the ionosphere at Jupiter. And I suspect you'll hear more about this as we go, but this is an example from Jupiter. And then even Mars, the crustal magnetic fields at Mars can create aurora there. And so you can get discrete aurora, which are the kind of pretty curtains that we see that, you know, most movies are showing, and then more diffuse kind of glow that is generated by different processes. And you actually get both at Mars too, which I thought was pretty interesting. Due to crustal magnetic fields, which we'll skip over a bit. Okay. Any questions here? We're close to time, so I will probably wrap it up here. I have a chunk more kind of comparative magnetospheres, but I think you'll talk about that in a lot more detail later on. And I also have a chunk on space weather, kind of actual effects, why some of us care. But maybe it's better to just pause and see if people have any, yeah, pressing questions or comments. Yeah. Great question. So the kind of large, yes. So what is a substorm? Hard to answer, but also how does it relate to that Dungy cycle that we just saw? And is that Dungy cycle what's creating substorms, or is it something different? So that large scale Dungy cycle that we saw of kind of the entire tail reconnecting and coming back in is typically geomagnetic storm related, because you're getting this kind of global change in the system on day time scales. Substorms relate, if you go back to that more complex picture, maybe. there's all sorts of finer scale structure in the tail. So you can get reconnection happening at different points in the tail across just narrow regions in the tail, not the entire magneto tail. And you can get that process generating this same picture, but on smaller scales, shorter time scales. And that is what I associate with substorm activity versus storms. Does anyone have other definitions? That it's a tricky question, and I think the substorm community is very, there is often a lot of debate within it, especially because it was originated from an observational perspective of looking at the aurora. And so you actually don't know what's happening in the tail when you call something a substorm. Yeah.
I've just heard of the different schools of thought as like the outside in versus the inside out. So whether or not that reconnection takes place first in the tail, whether it takes place closer to Earth.
Yeah. So if you've ever been to any kind of conference session on substorms, no one agrees. And there's also a big difference in what perspective people are coming from observationally, if they've been looking at aurora all their lives, or in situ measurements in the tail, or doing global modeling. Yeah.
How's SCP's effects on outer radiation belt?
Yeah, so solar energetic particles. Yes, so direct, very high energy particles from the sun can enter directly into the magnetosphere. SEPs can be both high energy protons or electrons, but typically slightly lower energy electrons. And so I primarily consider them as a source of high energy protons in the Earth's magnetosphere. And so these high energy protons can actually directly populate the inner radiation belt, which is proton dominated. And so they can act as a source. Yeah, as a very direct source. Yeah.
I've always been confused looking at cartoon pictures of the magnetosphere, but I've wondered where the plasma sheet sources to within the magnetosphere.
Yeah, so it's just like this blob in the tail, right? It's like where it comes on the inner edge or where it goes out extending to, or either.
I guess more so on the inner edge.
Yeah, on the inner edge. So the plasma sheet in those pictures usually just ends when you get to the inner magnetosphere, and then there's a bunch of like radiation belt, ring current, plasma sphere. That plasma sheet, so particles in it in the tail, say 10 Earth radii out, are maybe keV energies. And as they move inwards, they're just adiabatically accelerated through the magnetic field strength being stronger as they move inwards, as they convect inwards. And so they can turn into the ring current as they start to drift around the Earth, left or right. And so that's one place they go. They're kind of a source of ring current population, just energetically. Plasmasphere is too cold. Radiation belts are usually a little too high energy. So you need some kind of acceleration of the plasma sheet to get to the higher energies. But there have also been recent observations of injections of particles from the plasma sheet that might directly feed the outer radiation belt, so be high enough energy to just kind of contribute to that. So there's a fair amount of overlap in these terms and regions. Yeah.
Yeah, it was more for like a magnetopause like distance. Sometimes I've seen that the magnetic field is doubled at that distance, and I don't know if it was like what you thought about it, or because like the two pressures like equalize, but sometimes I saw like 2B like together squared instead of just B squared. I don't know if
in like the equation that gets you the magnetopause, or in observation? No, okay, the basic equation. I won't flip through all my slides to get back to it. Okay, excellent. Yeah, great. Then I'll just say pass. Yeah, great question though. Thanks. Here and then there. Yeah. I think, oh.
I just had a question about the influence of the interplanetary magnetic field on the magnetosphere. At least in simulations, we pretty much always neglect BZ, like the component facing along the direction between the Earth and the Sun. Sorry. I wondered if you could talk about what the influence of a significant BZ component is, how that affects the configuration of the magnetosphere.
Yeah, so in the coordinate system I typically use, BZ is
Sorry, I meant
along
BX.
the,
Sorry,
yeah,
I meant
along the Earth kind of north-south, but
I was talking
BX
about
is sun-Earth.
I always talk about BZ. So
Yeah.
BX, yes.
Yeah, and so BZ is the one you always hear about, but obviously it's not just like a line that's tips only this way and this way. You get BX and BY components. BY can cause a twisting, and BX and BY people are kind of starting to pay attention to more because we can't explain everything with BZ, and it can change that coupling. It can cause, you know, a shock to affect maybe one hemisphere differently than the other, or dawn-dusk asymmetries if you're in Y. So those are very important to consider and usually totally ignored. Yeah, yeah.
So I'm not very familiar with Mars, but you showed an image of discrete aurora at Mars. Like, does it happen only where the crustal magnetic fields are? And I couldn't tell the difference from those images you showed. So how do they determine that it's discrete and not diffuse?
Yeah, so these images, maybe it's hard to see in the pink pictures, but there is a teeny kind of more discrete line that you see versus just general glow. And it's even more obvious in the green, those more discrete lines that you see versus kind of general glow. And I believe, I'm not that familiar with Mars either, but that the discrete is tied to the crustal magnetic fields. Did you want to add to this? Yeah, yeah, wonderful. Yeah, thank you. Still pretty tied to crustal field locations. Yeah, yeah. Right. Okay. Yeah. Cool. I see a 2-minute warning, so I think let's wrap up. I'm gonna have to flip through like a bunch of slides, so just close your eyes for a second. Any last questions while I'm flipping? Okay. Okay, so I thought end on a few of my personal takeaways. One is that, you know, because I study the radiation belts, we often talk about the application and kind of space weather applications. But I think there's both the applied perspective, especially studying kind of star-planet interactions, as well as the interesting pure physics. And especially when you move into comparative heliosphere, magnetosphere systems, I think it's important to keep this in mind that, you know, studying our own magnetosphere can teach us about these other systems, and also these other systems can teach us about whether we truly understand our own. And then the other, you know, takeaway is just the system is very complex and interconnected. And that's both the beauty of it and the challenge of it. And being able to compare these different planets or different stars is one way we can get a better handle on how things interact with each other through this kind of turning it into a lab experiment, changing a variable and seeing what the downstream effects are. So those are my 2 takeaways. I didn't bring, well, I was going to pass around note cards, but we won't do that. I wanted you to just personally take a minute. We'll end with this and kind of think about one of your takeaways from this, something you learned or found interesting, and then also a question you had. If we have a minute, I'll go pass paper around. Otherwise, just, oh, sure. I find it interesting to collect them personally. No need to put a name or it. It's purely for me to find interesting. So, and also for you, I think it's been shown that if you kind of pause after hearing a big spew of information and think about it for a minute before moving on, you'll retain a teeny bit of it slightly better.